So today we're going to look at the second half of lesson 2-6. Pardon me if JoJo barks in the background, but she feels she needs to protect me from all intruders, real or imaginary. So 2-6 is on families of functions. So today we're going to concentrate on transformations. And so we're going to take a parent function, and here you see the y equals x squared, which is the quadratic function family. And we are going to translate or shift the graph horizontally, which is right left, vertically, which is up down, or both. So what I would like you to do is go ahead and put some ordered pair points at 0, 0, 1, 1, negative 1, 1, and 2, 4, and negative 2, 4. So those are those basic 5 points that we graph on this particular parent function. And then I am going to shift this, let's go 1 unit to the right and 3 units up. So for every point, I'm going to move, like I'll start with the origin. I'm going to move it 1 unit to the right and 1, 2, 3 units up. So I'm going to put a point right there at 1, 3. So there's my origin. And then I'm going to move this one 1 unit to the right and up 1, 2, 3. So that's going to put me right about there. And then I'm going to move this 1 unit to the right and 3 up. So that's going to be, I don't know, right about there. And then I'm going to move this point 1 unit to the right and 3 up, which will put me right there. Whoops, there we go. And then the final point, I'm going to move this 1 unit to the right and 3 up, which is going to put me right about there. So that's a really large point. So here's my shifted graph. And as you can see, the shape of the graph has not changed, except for the fact that I have a goofy point there. Should have been just a smidge over. The shape of the graph has not changed. We just moved it, and I like to look at a key point. So my key point on the parabola is the vertex. So as you can see, this vertex moved 1 unit to the right and 3 up, and so did every other point. So that did not change the shape or the orientation. Orientation meaning what direction is it turned, has it been reflected, that type of thing. Now let's talk about reflections. A reflection is essentially, and this is not a technical word, it flips the graph across a line. It could be, it's going to reflect over the x-axis. It could be a reflection over the y-axis. It could be a reflection over any other line. Let's go ahead and reflect it over the x-axis here. And all that means is we're going to put those 5 basic points on the parent graph. And I'm going to take each of these points and I'm going to count the distance they are from the x-axis. And I'm going to count them in the opposite direction and plot the point. So this one is 4 units away from the x-axis, so plot it 4 units away on the other side. So add some points here. So then that would mean I'd be right about here. And then this point is 1 unit away from the x-axis, so I'll have to go 1 unit away. So I'd be at negative 1, negative 1. And now 0, 0 is on the line of reflection, this being our line of reflection, so therefore it doesn't move. So 0, 0 is going to stay put. This point at 1, 1 is 1 unit away, so it's going to be over here at 1, negative 1. And then the last point is 4 units away, so we'll go 4 units on the other side. And so this would be a reflection over the x-axis. Your page. So as you look at the next page, we're going to talk about how do you know if you have a vertical stretch. Now let's talk about a vertical stretch and a vertical compression. So imagine that you are taking your fingers and you have this line like a string that is in control of this graph. If you pinch one set of fingers up here and another set of fingers up here and pull vertically up down, this graph is going to stretch and these arms are going to get closer to the y-axis. So in other words, the vertical stretch is going to make the graph look closer to the y-axis. So a vertical stretch might look something like this. The x values will not change, but the y values are now further away than the original y values. If you have a vertical compression, imagine that you're putting one hand flat here and one hand flat here, and you're pushing your hands together in opposite directions, kind of like if you were trying to smush something like a hamburger, trying to smush a hamburger patty. It's going to smash this down flatter. So these are going to go flatter in this direction towards this x-axis. So a vertical compression is going to make the graph look closer to the x-axis. So again, the x values don't change, but now the y values are closer to each other than they were before. So let's go ahead and look at some graphs and make some translations here. So on this first graph, we don't have the actual function equation, we just have the graph itself. And we're going to perform a vertical compression by a factor of 1/2. That means that if you look at this graph, the x-axis right here, this is the line that's in the middle, and I'm going to just draw like a dashed line right through here. So you can see that that's the middle of the graph. And that's important because I want to note some major points. So this is a major turning point, and it is approximately 1, 2, 3 units above this line. And so if I want to compress it, smash it down by a factor of 1/2, I want to reduce this distance by 1/2. So 3 units divided by 2, 3 units divided by 2 is 1.5, so that would put me right about there. And then all of these places where the graph crosses this red line, none of those are going to change. These are all going to remain the same. Imagine those as your zeros. So 0 times 1/2 is going to be 0. Then again, this is a major point, and it is also 3 units away. All of these are 3 units away. So I'm going to bring this point down 1.5 units. So I would be right about there. I'm going to do that to every single one of these points. I'm going to bring them down, shrink them down to 1.5 units. If you hear snoring in the background, that's JoJo sleeping on the chair next to me. I think she has sleep apnea. And I'm going to connect a line. And so you can see that this compression has brought the graph closer to this x-axis, just as I said above. Now this particular translation, we're going to have a horizontal translation, so horizontal lines go right, left. So a horizontal translation of -3 units means we're going to go to the left. So I would write that above here. That means we're going to go to the left. Let me move this down a smidge. To the left, 3 units. And then we're going to do a vertical translation. So vertical lines go up and down. So because this is positive, that must mean we go up. The reason why we went left here is because this was negative, and left on the x-axis are negative values, right on the x-axis are positive. So for a vertical translation, a positive number would be up on the y-axis, a negative would be down. So this positive 5 is going to force us to go up 5. So again, this is a funky looking graph. I would choose some very distinct points on the graph. So I'm going to put a point here, and a point here, a point here, and maybe a point here. I want to choose points that cross grid lines that are not in the middle of grid lines. And I'm going to take each of these points and move them left 3, up 5. Now this point, I'm off the graph, so I'm not going to actually move this point. But this point I'll move left 1, 2, 3, and then up 1, 2, 3, 4, 5. So I'm going to place a point there. Alright, so I think it's right about there. That looks about right. And then I'm going to move my next distinct point left 3 and up 5. So that would put me about there. And then finally I have this point. I'm going to move left 3 and up 5. Okay, so I'm going to try, now you should be connecting these with a straight edge. I can't do that on this, but I'll try my best to connect these points. And you're going to notice that the shape of this graph does not change, just its position on the coordinate grid. So that's about all you have to do on those types of questions. Then you might get a question that looks like this. You're going to be given the parent function, which is your linear family, y equals x. You can choose your x values. I highly suggest for this particular function that you choose our favorite values of -2, -1, 0, 1, and 2. Just because those are some negatives, 0, and some positives, and they'll hit the middle of that graph. So the parent function would be your x is exactly equal to the y. So this is going to be your y values down here. So I'm going to put my parent function in, let's see, in an orange color. So my parent function is going to be in orange. And so since this row represents my y values, since x is equal to y, then there's no change. So I would have -2, -1, 0, 1, and 2. And so I'm going to plot those points on here, and I'm going to try to make this bigger. Oops, I did not want that. All right, so that's just so it's easier for me to graph. All right, so then -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. And then you can finish out that pattern because it'll help you create a straighter graph. Okay, and so I'm going to leave the parent graph in a dotted format like this because what I really want to look at is the translated graph. So I'm going to put the translated graph here. You can see the only thing that's different is we have added 3 to the x value. So if I take every x value here and add 3 to it, -2 plus 3 is +1, so that's my new y. -1 plus 3 is +2. 0 plus 3 is 3. 1 plus 3 is 4. And 2 plus 3 is 5. So I'm going to plot this row with this row. So I have -2, +1, and -1, +2, 0, 3, 1, 4, and 2, 5. So then you can see a pattern forming, and you can go ahead and finish that pattern all the way across. And I'm going to connect that. You should use a straight edge. Whoops, I cannot. All right, so then the only thing that you're going to look at is what has happened. So I would just choose a very specific point, and I'm going to look at these points right here. So I have one point that's 0, 0 and one point that's 0, 3. Notice that the x values did not change for both of these points. So 0, 0, 0 is here and 0, 3 is here. The only thing that happened between those 2 points is the graph moved up 3. That's it. So as you look over here at the question, it says, how is the function, this new function, related to the parent function? So each output, that means y, of the translated graph is 1/3 of the course. That would imply 1/3 is a vertical compression. So that didn't happen. Each output, which is y, is 3 more than the corresponding output for the parent function. That sounds about right. So let's put a circle around that for right now, but we're going to go ahead and read through the rest of them. Each output, which is y, is 3 less than. 3 less than would imply that we went down 3, and we didn't. We went up 3. So it can't be that. Each output is 3 times the corresponding output. 3 times implies a vertical stretch, and we definitely didn't have that. Because if this had been a vertical stretch, you would have seen the slope of this line change right here, because it would have gone closer to the y-axis, and that did not happen. All right, so let's look at 4b. You are going to graph the given functions, f and g, on one coordinate plane and compare them. You are to graph f with a dashed line and g with a solid line. So I am going to graph f in that orange, and I'm going to create an xy table here. So this is going to be our parent function, which actually is a translation of the y equals x graph, but we're going to just look at this particular one, y equals 3x, and look to see what is the difference between this and this. So obviously it's the plus 5. And I kind of want you to think about it. What is going to happen to this graph with the 3x plus 5? Is it going to move it up 5, down 5, right 5, or left 5? It is not going to be a vertical stretch or shrink, because we'll talk about that a little bit more in detail later. But we are going to use my favorite points, -2, -1, 0, 1, and 2. Why? Because they're small and they're going to work. All right, so I'm going to take -2, and I'm going to take all of these and substitute it into here. So -2 times 3 is -6. So -2, -6. Yep. All right, and then -1 times 3 is -3. And then 0 times 3 is 0. And then 1 times 3 is 3. And then 2 times 3 is 6. And then you can finish that pattern. Move this over a little bit again. You can finish that pattern throughout. So we're going up 3 to the right 1. I can do it on the other side, down 3 to the left 1. And then if I connect that as a dashed line, there we go. So that's our f function. And then the g function I'm going to put in blue. So I'm going to do an xy table over here for the g function. And I'm going to use the same x values. So note that our x values have not changed. All right, so we're going to substitute them in. And essentially, if I substitute all these into here, I get these values, and then I would add 5 to it. So I'm just going to take this function over here, and I'm just going to add 5 to each of these answers. So -6 plus the 5 is -1. So let me move this over so I can graph it. And so I have -2, -1. And then -3 plus 5 is +2. So -1, +2. And then 0 plus 5 is 5. So 0, 5. And then 3 plus 5 is 8. So 1, 8. And 2 plus 5, I'm sorry, 6 plus 5 is 11. I thought something was wrong. And then that one is not going to fit on my graph, so I'm not going to graph that one. And then I can finish the pattern below because each point is going up 3 to the right one, so I could go down 3 to the left one, down 3 to the left, 3 to the left. So you can see that these lines are parallel to each other. And I'm going to try to draw a straight line. That was pretty good. Okay, so again, you want to choose 2 points. So I'm going to choose, I don't know why I have that up there. I'm going to choose this point and this point. So I've got the 0, 0 here and 0, 5 here. And you can see that all that happened was that we went up 5. So when you add 5, so if this is our function 3x, and if you add 5 outside of that function, it forced that graph to move up 5. So what happened if it had been a -5? It would have moved the graph down 5. So outside the function, positive number moves it up, negative number moves it down. So it goes in the same direction as you think it would. So right here, it shifted it up 5 units. So the answer would be D. All right, let's look at your very last page. Okay, so on this page, what you're seeing here is a general form of any type of function. So this f just represents whatever the function rule is, whether it's x, x squared, x cubed, the square root of x, the cube root of x, the absolute value of x, whichever one of those parent functions that we looked at yesterday. That's going to be the function rule, if you will, that's going to be in place here. And then, of course, it's going to be in terms of x. So, and we'll look at some more specific ones here in a minute. If you add or subtract something inside the function, something's going to happen. So we're going to write that down. We already discovered what happens if you add or subtract something outside the function. So remember, the function is the function rule. And then this is going to possibly occur if you multiply something outside the function. And then if you have a negative, something happens. So I'm going to use the following function. So I'm going to use the following parent function, y equals x squared. So I'm going to use the quadratic, y equals x squared. And then let's just say that I had the following transformations. Y equals negative 3 times x plus 2 squared plus 5. So instead of this f, the function here is this thing being squared. So it's x squared. One of the things you're going to have to get used to is trying to identify what the parent function is. So I know that there's a lot going on in here, but the main thing that's happening is you have x being squared here. And then there's some translations that are occurring. You have a plus 2. This is inside the function because the function is x squared. So this is inside the function. The plus 5 is outside the function. And then this negative 3 is being multiplied to the function. So this will start with a negative. So this negative here, which is here, means that there would be a reflection over the x-axis. Okay, so if there's a negative on the outside of the function, it is going to affect the answer, which is y. And if y goes from positive to negative, you are going to reflect that graph over the x-axis because all of your y values will go from positive to negative or from negative to positive, and so it'll flip it one way or the other. All right, so this particular function will have that reflection over the x-axis. Then if you have a number in front of the function, like we have here, this 3, you have to look at it and determine, is it greater than 1 or is it between 1 and 0? Since 3 is greater than 1, we are going to end up with a vertical stretch. So I'm going to abbreviate vertical by doing vert. So a vertical stretch, which means it's going to pull the graph closer to the y-axis of, I'm going to just put A here, whatever that number is. So on our transformation here, our graph is going to stretch 3 times what it was. Okay? Now, if that number is in between 0 and 1, like we had on the other page, we were doing a vertical compression of 1/2. 1/2 is between 0 and 1. So if you ever have a fraction that's between 0 and 1, and mind you, if that fraction is negative, it's a reflection over the x-axis. So you have to ignore the negative and look at the absolute value of A. So if it's a number between 0 and 1, it is going to be a vertical compression, which means we're going to smash it. Okay. Then we're going to look inside the function. So on our example here, inside the function, we have a +2. Now, it is affecting x. So think about it this way. Inside the function is affecting x. Outside the function is affecting y because it changes your final answer. So inside the function affects x. X goes in a right-left direction. You would think that a +2 would move the graph to the right 2, but it doesn't. Oddly enough, it's going to move the graph to the left. So if you have x plus some number, you have got to learn that, and let me find a good color. I don't like any of those choices I have. Well, I guess we'll just do green. Okay, so if we have x, a positive value inside the function, it is going to move in the opposite direction of a positive, which would be left. And it's going to go left h units. If this had been a -2, we're going to go in the opposite direction of the minus. We're going to go to the right 2. So if your value inside the function is minus, that means you're going to go in the opposite direction, and you're going to go right h units. Okay. Now you might also want to put in here that this is the opposite direction of x. So it's the opposite direction of what you think it would be. All right, then let's talk about finally what happens outside the function. So outside the function we have a +5, and we just did that problem on the other page where we had that 3x and the 3x +5. Well, that +5 was outside the function and it moved the graph up 5. So outside the function affects y, and so y goes in an up-down direction, the y-axis. And so it is going to affect it exactly as you think it will. So since this is a +5, we would go up. So if you have a +k, you are going to go up k units. And if your k is negative, you are going to go down k units. All right, so of course, this is the same direction of y. Okay, so let's go back through this one more time. So based upon all of this, I know without graphing this equation right here, that I know that this parent function is going to, because of the negative, reflect over the x-axis. Because of the 3, it's going to have a vertical stretch of 3, which means that the arms of the parabola are going to stretch closer to the y-axis. because inside the function we have a +2, we're going to move in the opposite direction of positive and go left 2. And because of this 5 outside the function, it's going to affect y, and it's going to go in the same direction we think it will, which is up 5. All right, so then let's explore a couple things down here. Let's look at 2a. If g is a transformation of f, the graph shows f as a solid curve, so here's your f, and g is dashed, so g is the transformed curve. So I highly suggest, before you determine which one of these applies to g, the dashed one, that you pick a very prominent point on each one. So I'm going to pick the vertex on each one, and I'm going to look at those. So the vertex here went from an x value of 3. Notice that they did not move up from each other. I moved 1, 2, 3, 4, 5, 6 to the left. So we moved, whoopsies, we moved 6 to the left. So left is an x direction, and normally you would think left would be -6, but because it's inside the function, it's the opposite of what you think it would be. And so instead of a -6 inside the function, it is going to be a +6 inside the function. So A would be the correct choice for the equation of that transformed function. All right, so for it to have been this one, this graph would have moved down 6 because it's outside the function. If it had been this function, then -6 means the opposite of going left 6, which would be to the right 6. So we would have moved to the right 6, which it didn't. Outside the function of +6 means that we would have moved up 6, and the graph did not. All right, let's look at B. And so B, you have the graph on the left. That's going to be your parent function. It's a little funky. And then you need to write the formula for each of the transformations A, B, C, and D. So there's 4 different transformations that have occurred. And so again, I highly suggest you pick a prominent point. So I'm going to look at the point 1, -1 and see what happened. So as you look at A, here's that same prominent point here. And notice that the x value did not change. So we didn't have any right or left movement. It just went down 2. So down 2 is a y direction, which means it should be outside the function. So we are going to take f of x, because we don't know actually what the function rule is. We're going to take f of x, and because it moved down 2, that's outside the function, exactly as you think it would be. So it should be f of x minus 2. All right, so then let's look at B. So here's that same point on B. And if you notice, this graph is flipped from this graph. Notice that this point is 1 unit away from the x-axis here, right? 1 unit away. And then look here, it's 1 unit away on the other side. Look at this point up here. That point is 1, 2, 3 units away from above. Here's that same point below 1, 2, 3 units. It's been reflected. So this graph has been reflected over the x-axis. So this is a reflection over the x-axis. So to show a reflection over the x-axis, you're going to put a negative outside the function being multiplied to it, and that's all there is to it. And then let's add to A that this was down 2. Okay, so then let's move on to C. So for C, that same prominent point is over here. And so it moved from being right here, it moved to the left 1, 2, 3, 4. So we moved left 4 and down 1, 2. So we have 2, was it 2 or 3? Oh, it's down 3. So if we're right here, 1, 2, oh, it's actually down 3. My point is just in a funky way. So we are going left 4, down 3. So let's write that down. Left 4, so we don't forget. and then down 3. So here's our f of x. All right, so the left 4 is affecting the x because left is going in an x direction. So left 4, since it's inside the function affecting x, it's the opposite of what we think left would be. And so instead of a minus, we're going to put a plus 4. And then we have outside the function, we have this down 3. And because down is in a y direction, that's why it's outside the function. And that means that we're going to have exactly the same direction as we think it is. So the minus 3 will be right there. Then we just have one more on this question. And I'm going to look at this point right here. So that point right there, I can already tell you the graph is reflected because it's flipped like this one is. So instead of looking at this parent function, we've already reflected this graph. So I'm going to just look at these 2 points because I know for a fact that we have a reflection over the x-axis. So that's number 1. And then number 2, we have to see how did this point move to here. So this point is at 1, 1, so it's right here. So we must have moved to the right 1 and up 1, 2, 3. So we have right 1, which is inside the function, and up 3, which is outside the function. So we already know that we have a reflection, so that's going to be a minus f of, and then our x. And then due to this right 1, right is that x direction, and because that's inside the function, we know that's opposite of right, so it's going to be a minus 1, not a plus 1. And then up is a y direction, so it's outside the function, and outside the function is the same direction as we think it is, so then that will be a plus 3. And then finally, we have just words, no graph, and they are telling you that you have, that your parent function is the square root function right here. And they give you the function. So we're not going to use f of x, we're going to use f of x equals this. And so the first translation that they give you is that it is reflected over the x-axis. So a reflection over the x-axis means you are going to multiply by a negative outside the function. So let's start with f of x equals, and then we're going to have a negative outside the function, and our oh, that was terrible. Let's try that again. All right, let me make it prettier. Negative. Okay, try that all over. None of that looked good. There we go. Okay, so then we have the square root of, and then x. So here's our reflection over the x-axis. That's represented by that negative outside the function. Then we are translating it 5 units to the left. So let's do 5 units to the left is going to be in pink. And because left is an x direction, and that means it's inside the function, we're going to do the opposite sign of what left would be, and we're going to put a plus 5 inside the function. And that's it. So you are going to work on your homework. It's normal to be frustrated. This is a difficult section. It's the first time you've really been introduced to transformations in this degree. You just need to start to talk to yourself about how that reflection looks in the graph. How does it look on the function and all that kind of stuff. And don't hesitate to ask questions. I expect you to ask a lot of questions. I expect you to need a lot of help. So please seek me out, and good luck.